Let's start simple. You're just standing around, you're at the park, whatever, and something's moving. And you want to know how fast. Or maybe you work at a paper mill and the paper is running through the rollers, but how fast? You can't just put a wheel on it, it'll rip the paper. We need a non-contact way to measure the speed. Welcome to the video. Let's talk about lasers. You might think I mean like LiDAR, where we would shoot a laser and would wait for it to bounce back, and then we'd measure the time that it took. But that's not gonna work. The paper is always the same distance away. Well, we can do something much more clever than LiDAR, which can measure the speed. But how? I'll give you a simple explanation, which is the way I thought it worked when I first researched this. That explanation turned out to be a total lie. But don't worry, I'll build on it and give you a deeper understanding of how lasers actually mix with themselves. And I'll even show you how to use a simple laser to measure speed. Let me introduce you to the hidden world of self-mixing laser velocimetry. Okay, you have a target that's moving. We'll draw it just like a wall, and you shoot a wave at it. The wave is going through space. It's an electromagnetic wave, so it could be visible light or any wavelength really. For our purposes, we'll say it's a red laser. And that wave is moving along and it's hitting the target, and that's it. That's all you need to measure the target speed. But how? Well, imagine you're a little tiny person living on this target here. If you were this target, you would see a frequency. And then if you were moving away, the frequency would be a lot lower. You can kind of see that here. If you were moving towards, then the frequency would be a lot higher. The perceived frequency of the wave depends on whether the target is moving. You may remember this from physics class. It's called the Doppler effect. Now, I promised you that we can measure the speed with no equipment, just the laser. So we're going to need to look at the reflection of this wave. What does the reflection look like? Well, you can picture a wave going through the target like it's a piece of glass. Now, our target isn't glass, but it turns out the reflection will be just a mirror of the green wave. So it just bounces back just like a mirror reflection would. The animation of this looks the way you'd expect. The red wave is hitting the target, the green wave is going back the other way. The key thing to notice here is that because the reflected wave is just the wave that would have appeared on the other side of a glass, it also must start from wherever the red wave hit the target. In other words, the wave must be continuous. This always has to be a singular point. You can prove this from Maxwell's equations, which we won't do here. This one constraint gives us a visual explanation of the Doppler shift. You can see that if the target's moving to the left, it will make the frequency of the reflected wave much higher than the original frequency was in the red wave. The frequency is purely driven by the fact that the wave must continue to stay intersecting wherever the red wave hits the target. And that just happens to be changing faster as the target is getting closer, or slower if it's getting further away. It's tempting to think that we can just measure the frequency of this green wave and compare it to the frequency of the wave we sent out and get the velocity that way. In fact, we could. Except, remember I said we use a red laser? Well, that puts the frequencies at a couple of hundred terahertz, which is at least 10,000 times faster than what a computer can measure. So it's way too fast for us to be able to do anything useful with it. Why didn't we pick radar, you might ask, with much longer wavelengths and frequencies that are down in the low gigahertz? It won't work for our paper example because of the way that the wave reflects off of surfaces. I'm gonna do another video on this topic, but for now, let's just assume we're stuck with the laser. So are we out of luck? No. we can do a new trick by drawing a new wave. In physics, the solution is always to draw more waves. We're just gonna draw this blue wave. The blue is just the sum of the red and the green. It's the superposition of the two. Now, it seems like we've invented something new, but actually we haven't. You can describe the waves by their sum. It's the same thing. So instead of looking at the red and green wave, we're just gonna look at the blue wave and say that that describes both of them. We're gonna focus on the blue wave and see what happens. We have the same animation as before, with the wave hitting the target and the wave bouncing back, and yet, what do you notice about the blue wave? It's not moving. This is what we call a standing wave, because it's standing in space, and it's oscillating up and down, but it's not traversing anywhere. So for a static target, this is what happens. It's gonna oscillate very fast, like at a terahertz frequency. But that's okay. Watch what happens when we start moving the target. Now, this is super cool. The standing wave will stay offset from the target and move with it. It has this property where it's always going to have this offset, and it's going to move along with the target. No matter how fast the target moves, it's going to move along with the target at that rate. And this is very useful, because when you're moving towards the target, you see the green line seems to move very fast, but the standing wave doesn't care. It just moves with the target. And if we move the other way, the green line looks like it's not moving at all, but the standing wave just moves with the target. At the beginning, I told you we were discussing self-mixing. This is what I meant. The laser is shooting light, which is reflected back, goes back into part of the laser, interferes with itself, and causes this interference pattern. Even at higher frequencies, it doesn't matter what the frequency of the light is. You can see I've made the frequency much higher, but still the standing wave, although it oscillates faster, it moves with the target. So this is super cool. It seems like we're pretty close to solving our problem. We just need to measure the blue wave. To measure it, we'll put a photodiode on the back side of the laser. And this will measure the total sum of the two waves, which is the blue wave. I'm going to show a simulation of the same system, but we're going to plot the photodiode reading over time here on this graph. So the y-axis of the graph is going to be the intensity of the light that's measured by the photodiode, and the x-axis is going to be time. Can you predict what it'll look like? You see this interesting pattern. So we see the faster oscillation up and down, which is the terahertz frequency we discussed before. However, you see this slower pattern of small amplitude, small amplitude, and so on. This is called a beat frequency, and it happens at a lower frequency, which corresponds with the rate that the target is moving. If the target moves faster, those beats would happen faster. If the target moves slower, they would happen slower. Now, this is something we can measure. Now we have a device that can measure the actual speed of the target, and that's the basics of the operation. That's the principle. And our problems would be solved except for one more minor issue. The blue wave doesn't actually exist. I lied to you. It's conceptually useful, but it's not quite accurate. To understand why, you need to understand how a laser works. The laser is basically just two mirrors, where one mirror is slightly less reflective than the other one. And then there's this medium where we put a voltage into it. And all that happens is that the voltage in this medium gets all the atoms super excited, and they start moving around, and some of them start emitting photons, or light. Before you know it, each photon hits another atom, which emits a photon, which hits another atom, and it cascades. And it gets in this feedback loop where suddenly all the photons are moving. But when they go up or down, they just hit something and kind of stop. But if they go left or right, they hit a mirror. And before you know it, they're all just jumping back and forth, right to left, never up and down. And what you create is this wave that travels right to left between the two mirrors. Now the mirror on the right is almost 100% reflective, but not 100%. And so eventually, when the light gets bright enough, some of it escapes through that mirror. And that's where it comes out of the laser. But inside the cavity, most of the light, it comes and it bounces back and continues. Now, hopefully this looks familiar to you. It's the same as what we just did a second ago. A wave goes out, it comes back, and then what does this create? Our good friend, the standing wave. How cool. The laser itself is a standing wave inside the laser cavity. Obviously, none of this is to scale. This is super tiny, like microns wide. The important takeaway here is that the wavelength itself will always be some multiple of the laser cavity length, because it likes to be centered sort of at 0, and it's 0 here and here. Imagine it's pinned on both sides. Therefore, the laser frequency is based on the size of the cavity. Now, why are we talking about this? Well, if we go back to our laser shooting at a target, when we talk about self-mixing, this system is not just an external cavity that's bouncing back. It's actually two cavities. It's the original laser cavity, which I'm going to draw on the left here, and then the external cavity, which we're trying to measure, which is on the right. So our laser is generated inside of this cavity, and it's going to have, in this case, two peaks inside of the cavity. And it's going to send itself out, and of course, it's going to hit the target, right? And then it's going to bounce back. The green reflection wave I drew, and I dashed it so that you can see it's on top of the red, is going to bounce right back. Remember I told you the blue superposition wave was a lie? The blue wave doesn't exist at all. And the reason is because of the way the light interacts when there are two cavities. When we draw it like this, you can see that we essentially have one laser with two laser cavities. Because of this, we can only have one wave, because it's one big laser cavity, split with a mirror in the middle. Just like inside of a single laser cavity, this dual cavity system needs to have one cohesive, coherent wave. That means we can't have these two independent waves. So what happens? I want you to watch for when the green and red waves line up into one single wave. Notice that they line up whenever the target hits the waves at a peak or a valley. You see this? Boom, they line up. Every time it hits a peak or valley, they line up. We don't just have a laser sending light out into space. We have a laser sending light out, and then we have another cavity with another mirror. Now, it's a bad mirror because maybe it's just some aluminum or some wood or who knows, but it's still a mirror. So it's still reflecting some light back. The way it's solved, the waves will always snap together like that. They will always stay aligned. And so every time the target moves, it has to snap to the peak or the valley, as if there's a spring tying the red and green waves together. They spring together. So what does this mean? How can we measure anything if there's just one continuous wave? Does this mean that when the target moves, it has to jump in half wavelength increments? No. Obviously, the laser can't physically force the target to stay in a particular location. So what happens when the target moves slightly? The way to imagine this system is there's not light going out and reflecting back later. Instead, the whole thing solves as one cohesive wave that exists all the time. The laser will align itself. And the way it will do that is by shifting its frequency. So let's say the target is here and nothing is aligned. Watch the red wave closely. To solve the alignment, the red wave is going to shift frequency ever so slightly until they align. Remember I told you that the frequency of the wave in the laser is a function of the length of the cavity? What we've done is we've said the same is true for this larger laser with 2 cavities. It's depending on where the target is, it will change the wavelength ever so slightly. We change it in order to make the alignment happen. You can see this in the red wave, by the way. If you look right here, it was aligned, and then it has to just misalign with the laser cavity mirror ever so slightly, and then everything lines up. Let's get rid of the green line because we know it's always going to be the same as the red line because they're going to be aligned. And now we just have one wave. So how does this work? When the target moves closer, is the frequency just going to scrunch forever and get smaller and smaller and smaller and smaller? If the target goes further away, will the frequency increase and spread out forever and ever? Pause the video and take a guess. What do you think is going to happen if the target gets closer or further? The result is so beautiful and elegant, but it's not intuitive until you see it. As the target moves, the laser just jumps. It squishes and then it jumps. It squishes and then it jumps. In other words, the frequency will get squeezed until it gets to the point where it has an easier frequency to be at that's closer to what the mirrors want it to be. The way to understand this is that the mirrors are dominating the situation because they're almost entirely reflective and the target out there is only giving a small amount of light back. The mirrors are a much stronger feedback. This means that the mirrors set the nominal wavelength and the nominal frequency, and then the frequency can be shifted slightly by the target moving. That will cause the wave to jump up and down, peak to valley, peak to valley. As you stretch back out, the same thing happens. You see the same effect. So the way we're measuring this was correct. We're still going to use the photodiode, but what we're going to measure is not going to be that nice wave I showed you with the beat frequency. We're actually going to measure the fringes. I don't know why, but they're called fringes. When the wave jumps, it's called a fringe. So every time you see the wave do a jump, it's a fringe. Here I'm showing you a plot. It's a great summary of what's actually going on. On the left, you see the distance from the target. It's increasing in red and then in blue, back the other way. Now on the right, the black line is what you would think would happen, which is the result I showed you the first time. It's a smooth sine wave, it's the beat frequency, everything is great. It actually moves on a stair step because when it's going away, for example in red, it can't go down. It can only go sort of across, but it just pauses and then sort of jumps to the next phase. Then it kind of travels along, then jumps again. And then if it's going the other way, it travels along the black line and then it jumps, travels along and jumps. The math behind this is so cool, but there's no need to get into it in this video. So now we have a speed measurement strategy. I didn't derive the equation for you, but I show it to you here. What's great about this equation is the only variables we need are the design of the laser, which sets the wavelength, the velocity, and the angle. So if you know the angle that the laser is mounted at and intersecting the target at, you can measure the frequency of the fringes and you will know the velocity. So for our paper example, as long as we know the angle, you multiply times a known wavelength of the laser that you're using and count the fringes, and then you know the velocity of the paper. I'm going to show you how we actually count the fringes, and then you'll have the entire picture of how you can use a simple laser to measure velocity. I'm just going to plot 1 second of data, kind of an arbitrary amount of time. And I'm just going to plot the voltage of the photodiode. Now remember, what this voltage represents is the power or the light intensity of the laser in the laser cavity. Therefore, it's some arbitrary number because the laser is on. In this case, it reads 3 volts. But then it has these blips. Now, these are the fringes. These are the pulses that correspond to every time the laser jumps. There's one more caveat to this, which is that in the real world, it usually doesn't look like this at all. Usually, it's very noisy. So the signal looks more like this. It looks like total garbage. But believe it or not, we can still get useful information out of this. If you squint, you could still make out the fringes in the simulation. I just put in 10 of them arbitrarily, so there's 10 pulses in 1 second. So a fringe frequency of 10 hertz. One of the things we need to do before we can measure frequency is shift this down. It's gonna make it a lot easier to see. And so now you can clearly see the fringes again, even though we have the same amount of noise. All we did is we canceled that 3 volts because the 3 volt offset isn't useful to us. It's just the laser being on. And so the signal is in the change in the voltage, not the actual voltage being at 3 volts. Now, we can take this data and run it through an FFT, which stands for fast Fourier transform. I won't cover the details of an FFT and how it works, but it will tell us how much of each frequency is in our signal. So we're just gonna plot it in hertz on the x-axis, and we're gonna plot the amplitude. This plot is gonna show you how much of each frequency you have. So if you have a 1 hertz sine wave, you'd see a spike at 1 hertz. Let's say 100 hertz, then you'd have a spike at 100 hertz. Great, we have this plot now. Most of this is kind of random noise at the bottom. This is the noise that I put in earlier, but we see 2 big spikes here. And these 2 big spikes are gonna correspond to the fringes that we see that are very hard to see because it's kind of noisy, but they're still there. The FFT is very good at finding frequencies in noisy data. Now, we're gonna have to shift the axes to the left. We're gonna shift down so we can zoom in, and boom. This is the 10 pulses per second, and we see a spike at 10 hertz. Now you might be wondering, why do we have one at 20 hertz? This is called a resonant or harmonic frequency. You can think of this like a ringing. If you had a musical instrument like a piano, you'd get the main frequency, then you might get a frequency that's double that or another triple that, and so on. In this case, we have one at 20. And we also have one at 30, but it gets kind of lost in the noise because they drop off and get less strong as you go. The 10 is what we care about. What's cool here is it seems like we haven't done anything fancy, but actually what we've done is come up with a strategy with only 3 steps to measure speed. 1, subtract the DC offset. 2, calculate the FFT. And 3, find the fundamental frequency peak. With those 3 bits completed, we know the fringe frequency and therefore the velocity. So that's it. We just created a way to shine a simple laser on an object, measure the object's velocity with no equipment on the object, and we just measure the laser's intensity. My favorite part is this can work at any distance. As long as you get enough light back to measure it, it will work. There's also a way to measure the distance to the target, not just its velocity. In fact, we can even measure the velocity and the distance at the same time, and we can even figure out whether the velocity is coming towards the laser or away from it. There's so much potential for this technology, but this video is already getting kind of long, so we're gonna stop here. Let me know if you would like to see a video discussing some other applications. Hopefully this video helps clarify some concepts that I know I found initially very confusing about self-mixing laser measurement. Let me know in the comments if anything wasn't clear or suggest topics for future videos.